Welcome back, everybody. So for the next video, it's going to kind of relate to 4.1 as well as 4.5. So I'm just going to kind of put both sections in there. But this is going to just deal with different integration techniques. So I did a video on 4.5, and this is just going to be kind of an extension of that with some additional exercises. So we'll start with number 1, which is going to be the integral of x divided by rad x plus 3 dx. So we've got a ratio of two functions, a linear function and a radical function, and we want to find the antiderivative. So we're going to want to probably use a u substitution, although if you look carefully, you might be able to see how to work backwards without, but nevertheless, we'll start with a u substitution. So let's go ahead and get into it. So u is going to be x plus 3, obviously. That's our composite piece inside of the square root. And du is going to equal dx. And we still are going to have this x floating around in the numerator, so we're going to want to back substitute and solve for x as well, which means x is u minus 3. So those are our three pieces that we need to substitute here. So let's go ahead and do that. So x is just u minus 3 all over the square root of u times du. And now we can just work, since I'm dividing by a monomial, to split the integral into two separate terms. So this is going to be equal to the integral of u over rad u minus 3 over rad u du. You could do two different integrals if you want to, but we're going to do it piecewise anyway. So we'll just note u over rad u is just radical u, so u to the 1/2, since this is u to the first minus a half. And then minus 3, and then u to the negative 1/2. So again, rewriting with rational exponents can make it easier to evaluate. So then we're going to have u to the 1/2 is going to become u to the 3/2 times 2/3, but our u is just x plus 3 minus 3, and then we'll have u to the 1/2 times 2, so our 3 is actually going to become a 6. And then we'll add our little plus c on the end there, and we'll have x plus 3. So there's our first just kind of generic substitution. So what I want to do is I want to take this example and maybe ramp it up a little bit. Make it a little bit more messy. So let's go ahead and do that. So now we're going to consider a second example, the integral of x plus 3 over the square root of 3 minus x. Right? So I still have a linear term over a square root, but I'm making the expressions a little bit messier. But the process will be the same. So we'll let u be 3 minus x, which means du is now negative dx, because I have negative 1x there. So it means that we're going to move the negative to the du side. And then we'll again solve for x, which is going to be 3 minus u. So evaluating that with our substitution, let's see what we get. So we're going to get x is 3 minus u plus 3. So we'll substitute in the numerator. We'll get rad u again, and then we have negative du, so I'll put the negative on the outside here. So now we've got negative. We can combine terms, so we'll just note that the top there, 3 minus u, is going to become 6 minus u. And then now we're in the same boat that we were with the previous example. So we'll have 6 over radical u minus u over radical u du. And now we've got negative. Now we can evaluate. So the 6 over rad u is going to become 12 times radical u. And then this is going to be minus, this is u to the 1/2, so we'll have 2/3 u to the 3/2 plus c. And then we can just substitute. So I'm going to rearrange terms here since we have this negative sign. So we'll do 2/3 times 3 minus x to the 3/2 minus 12 times 3 minus x to the 1/2 plus c. So you can see that there's a lot of different variations that can work this way. All right, so let's go ahead and move on to a different example that is still going to sort of be similar, I guess. So we're going to do the integral of 4x squared times the square root of 3 minus 2x. So we'll note here we've got a linear and then a quadratic, so a direct u substitution isn't going to work out nicely. So note if I had, say, a cube here, I could get a 6x squared and work this out, and it would be a little bit nicer, possibly. But this one's going to still be using the same idea. Let your composite piece on the inside be your u, and then work from there. So du is going to be negative 2 dx, which means negative 1/2 du equals dx if we divide by negative 2. And then we're going to still need to solve for that x squared term because we can't substitute it with either of these expressions that we've worked out here. So we'll solve for x. So we'll note we could subtract the 3 over. So u minus 3 is equal to negative 2x. And then we could divide by negative 2. So x is going to be u minus 3 over negative 2. But maybe that negative 2 is better distributed in the numerator. So we'll just note that that's the same as x is equal to 3 minus u over 2. So then now I've got all the pieces I need to substitute. So we're going to substitute these 3 pieces inside, and let's see what we get. So we're going to get the integral of 4 times x squared. So let's note x squared is going to be 3 minus u squared over 2 squared, which is just over 4. So you can see why I put the 4 in the original integral there, just to make it work out a little bit nicer. All right, so we're multiplying those. Oops. And then that's going to be times the square root of u du. So our 4's will cancel. And what we'll be left with is the integral of 3 minus u squared rad u du. And then at this point, 3 minus u squared is a pretty small calculation to make, so I'm going to just distribute that out. So we'll have 9 minus 6u plus u squared, all times rad u, and then I'll just distribute the square root of u into everything. So we're going to have the integral of 9, let's see. Let's use rational exponents. 9u to the 1/2 minus, so that's going to be 6u to the first times u to the 1/2. So it's going to be 6u to the 3/2 plus, now u squared times rad u is going to be u to the 5/2 since we add exponents. And now we're ready for our answer. So let's see what we're going to get. So we're going to get the u to the 1/2 becomes 3/2 times 2/3. So 9 times 2/3 is 18 divided by 3, which is 6. And then note we'll just plug in our u, which is 3 minus 2x. Our u to the 3/2 is going to become u to the 5/2, so that's times 2/5, which is going to be 12 over 5 when we multiply that by 6, plus, I'm running out of space here, but I think we can fit it. We'll have u to the 7/2, so this will be 2/7, since the coefficient here is just 1, and that's 3 minus 2x, 3 minus 2x, plus c. Don't forget the plus c. So again, a little bit longer example, but the same idea, where you're just modifying and then combining in some way. In this example, we multiplied it out, but in the other example, we split our expressions into separate fractions. All right, so let's go ahead and do a couple more. So for number 4, let's go ahead and do a trig example. So we'll do sine x plus cosine x squared dx. And this is going to be a simple one where we just expand it out. So go ahead and expand it out and work it out on your own first. So what we should get then is sine squared x plus 2 sine x cosine x plus cosine squared x. All right, so then we can rewrite this as sine squared x plus cosine squared x plus 2 sine x cosine x. So just rearranging terms here, and obviously I'm doing that because sine squared plus cosine squared is equal to 1, so that's just 1. And we could use the fact that this is sine 2x, that double angle identity I mentioned the other day, but let's just leave it as is so that we can just work it out. So we'll split this. So this is going to be the integral of dx plus the integral of 2 sine x cosine x dx. So that there's just a 1 here, but we don't have to write the 1 in. So the first term is just going to be x. So we know it's going to be, x plus whatever our integral is on the right. And so for this one, we could just do a quick u substitution. So we'll let u be sine x, and du is equal to cosine x dx. So we can sub both of those terms out. So this is going to be plus the integral. I'll bring the 2 outside since we can just leave it there. And we'll have u du. So then what we'll get is x plus 2 times u squared over 2, but the 2's will cancel, plus c, which is going to be x plus sine of x squared plus c. Okay. Which is a slightly different variation than if we did sine 2x. Right? So if we did sine 2x, we would get cosine 2x, and we would have to kind of reorient our expression a little bit. But we will get that this will work out the same way. All right. So looking here, I've got some definite integrals. So why don't we get to one of those? So we'll look at another interesting example. Let's see, number 5, we'll do the integral from 0 to 1 of the square root, the square root of x times the square root of x rad x plus 1. All right, so we've got kind of a nested set of roots here, although this is just a single term, so it's x times rad x. So it's not like an infinite nested term. So let's go ahead and take a look at this and see if we can figure out how to work it out. Inside my radical that's more complicated looks like what our u should be. So let's go ahead and give that one a try. So we'll just note that this is just the same as x to the 3/2 plus 1, since x to the first times x to the half is just x to the 3/2. So du then is going to be 3/2 u to the 1/2 du. Which, not u, sorry, x to the 1/2 dx. Mixing up my variables here. So we can substitute that out, so we're good. And we'll get 2/3 du is equal to rad x dx. All right, now we do need to change the limits of integration though. So x is 0 and x is 1 are my 2 limits. And those are going to become, let me just do some arrows. U equals, so 0 plus 1 is 1, 1 plus 1 is 2. So really nice values that this changes to. And what we'll end up with is the integral from 1 to 2 of u to the 1/2 du. So this nested expression, which looks pretty ugly to try and evaluate by itself, actually turns out to be pretty simple. And so what we're going to end up with is 2/3 u to the 3/2 from 1 to 2. So we'll get 2/3. So u to the 3/2 evaluated at 2 is going to be the square root of 8 minus the square root of 1, which is the same as 2 radical 2 minus 1. So we'll end up with 4 rad 2 minus 2 all over 3, or some equivalent expression. All right. So I think we'll stop here with this example. I might end up doing a few more, we'll see. But just a couple of different variations on examples where you're going to have slightly messier U substitution examples with just polynomials, radical functions, or trig functions. So if you have any questions, shoot me an email. Otherwise, until I see you next time.